So this is about our recent work that I will be talking about with Siraj, Labnit, Rohan, Angsuman and Sayantan. These are the things roughly. Huh?
Yeah, ICTS requesting you to mute your mic.
Naveen, Naveen, please mute your mic. Naveen, please mute your mic. Naveen, I have sent you the presentation.
Should I go through?
Got it.
So these are the things that I will.
Little louder, nobody will hear you.
So these are the things that I will roughly go through. First, I will quickly review this Sachdev-Kitayab model, and then the tensor model that we talk about goes by these names, and then I'll discuss the things that we did on the papers and these two things. We will talk about some new light modes that we have found, and then we will also mass deform the theory, and then we will try to see how the density of states goes, or if there is any phase transitions. So this is the action for SYK model written in Euclidean time. This is one dimensional, where this is the kinetic term, and then you have this interaction. This q of the q number of fermions are interacting. Q could be any even number, and this is the interaction strength, which is the dimension of mass in one dimension, and this is chosen from a distribution, a Gaussian distribution with zero mean, and this is the variance, where Z sets the strength of the interaction, and this power ensures that in large n limit we get sensible graphs, sensible large n limit. Now, in this action can with these things are like, if you take one of the choices, then you get a theory which is unitary. Now there are lots of them. They are fluctuating with this distribution. So you can write this rewrite this action through disorder average, and you can write it so that it is suitable for large n calculations. And that action, if we go into deep IR, which is in this case J going to infinity limit, and we will see that in this action, if we just ignore the kinetic term, which is irrelevant in this limit, then that action has some diffeomorphism 1 invariant. That has diffeomorphism 1 invariance. It will look something like, that action will look something like this action here, except that the indices will not be there. So if we ignore this term, this rest of the part is diff1 invariant. And
sorry, what does that mean exactly? It's diff invariant because if you take sigma of, what is the action of diff s on sigma of t1 t2?
yes, so this is the action that you will get without these indices.
Now, Sandeep is asking, how does diffeomorphism act on sigma?
Yes, so in this thing the
Is it here? Okay,
no, these are different things.
Okay.
So I'm talking about this SYK model. So these diffeomorphisms act like this. Yes, the reparameterizations. That's the reparameterizations, and the sigma goes correspondingly.
Similarly,
Yes, just to the power q minus 1, so that when you substitute it back here, 2 factors from here, from the f is the arbitrary diffeomorphism you are taking, that will get cancelled. So this is the.
And if you look at just the original action here,
Yes.
if you drop the kinetic term, then that clearly has a wild invariance. If psi scales like,
t to some suitable part.
yeah, and then once it's wild invariant, it's also all diffeomorphisms in one.
Thank you. Got it. Yeah, that's what you're seeing here, but that's
Yeah.
much clearer. Yeah, thanks.
And this is about j going to infinity limit. And then if you calculate the classical large n, in strict large n, if you calculate the equation that you get, the classical gap equation, then it has solutions of this form. The 2-point function has this structure in strictly j going to infinity limit. This thing is true. Now, if this solution came from an action which has deformed invariance, but this classical solution that we are taking here, this is not invariant under arbitrary diffeomorphisms, but only under SL2R subgroup.
So again, sorry, last one. So in the large n limit, this is what you get in the deep IR.
Yes.
And then this preserves only SL2R. Okay.
Only SL2R. So that
it doesn't preserve the full diff.
no, it does not preserve the full thing. It just preserves SL2R part of it.
I mean, it's COVID. Oh, but that's because you got a temperature, right? I mean, is that your point? I mean, sorry, I didn't quite understand. I thought there was an argument that in IR you would have the diff as well.
I think he's saying diff is spontaneously true.
No, at finite temperature.
Even at 0 temperature, it will be true.
You see, it's very hard to get a function that is diffeomorphic in it.
Okay, but I mean, at least from the black hole point of view, the ADS2 symmetry is broken because of the finite temperature, right? I mean, here, can I just look at this and see what you're saying? If I take beta to go to infinity, of course, I get something kind of.
You get a power.
Oh, you get a power?
Yeah, you will get like if you take beta goes to infinity, then it will just
I
become
see, okay.
to
But
the
if you
total.
get power, then don't you have that symmetry?
You have only SL2R with this.
Suppose you take t goes to an arbitrary function of t. It clearly changes its form more literally.
It's covariant or something, but that's what you were saying is. I'm sorry, just to understand.
This thing it transforms as an f prime.
So if you make this transformation here with arbitrary functions, then this will just change.
But okay, under t goes to f of t, you say this is a different transformation from what would have been needed. I see. But this is just the anomalous dimension in a sense. I mean, this is the operator picking up some
Yes, yes,
dimension, right?
yes. It
That's the operator. Yeah.
Which is, I thought just, I mean, here, the fact that it's going like t to some power is the operator picking up.
yes. So
some
in deep IR, this high fields pick up this anomalous pick up this dimension, whereas in naive dimensional counting will show their mass dimension 0. So in IR they picks up this.
I mean, it's like in 2D CFT. The Virasoro algebra is broken by that.
Now,
I mean, the vacuum preserves only an SL. It's like that.
yes, so it's like the action has this symmetry, but classical solution has broken this thing, and then you expect if you take the action for deformed coset by SL2R, then you will get something non-zero even at j going to infinity, but this is explicit calculation shows that this is not the case. So if you stay at j equal to infinity, then the action for these generators is just 0. So if you want to get some action which is a non-zero, then you have to break this conformal invariance and go little bit away from j going to infinity. So in 1 by beta j order, you will get something non-zero for these modes. So it's like the pion mass term. So
that part I understand why you're getting an action, but I was a bit confused by the statement that you broke the symmetry even at 0 temperature. That is, even where j goes in your language, j times beta goes to infinity, so you don't have an action.
You don't have that. So
You were saying even at 0 temperature, where you're saying the action vanishes, the coefficient of the action vanishes.
yes,
Even there, we are breaking the symmetry spontaneously.
right.
yes. So it's like the kinetic term that you would get in spontaneous symmetry breaking. This kinetic term is 0. When you go little bit away, like explicitly you are breaking the symmetry, not only spontaneously in 1 by j you are breaking it explicitly also, then you are getting the mass term, which is the non-zero action that I am talking about.
Yeah, except that in a usual Goldstone mode, if
Yes.
you break it spontaneously,
Yes,
without
it's
an
different.
explicit breaking, you would have gotten an action.
Yes, so this action is 0 here. So we are getting it for explicitly breaking.
That's different because this Goldstone mode in time. You usually get it in the usual Goldstone mechanism. You get it because if you did just a variation on configuration, it's a 0 mode, and then you allow it to vary slowly in time, and that gives you an action. Right? But sorry, just the fact that this breaks the invariance, is that clear even at 0 temperature?
I'm still confused from the gravity side. Maybe we can talk about it later, because if you have ADS2 with a boundary, I mean, where is the bulk doesn't break it. Okay, well, we should come back to that later. Okay, maybe I'm just confused.
Okay, so and then there are further studies with this. The action that we get for this diffeomorphism is the Schwarzian action, and then there are some studies in ADS2 to get the dual description in terms of ADS2 gravity, and that is by Gautam, Spenter, Nayak. There is this paper, and there are many other papers like Pulczynski, some back reactions, but yeah. Then if you look at this thing, this is in imaginary time. This is tau, sorry, this is just this tau. So if you go to the Lorentzian time, then you see t going to infinity will give you 0 because sin will become sin h. So this model self thermalizes, and then if you calculate this quantity here, which is this out of time ordered correlator, suitably these y factors are just the density matrix used for regulating this correctly. And then if you calculate thermal average of this guy, then in 1 by n correction you get an exponential growth like this, and the exponential growth in j equal to infinity, like at strict conformal limit, is 2 pi by beta. This is the maximum that you can get. So so these two properties, the first one that it thermalizes, and this one that this is like saturates chaos bound, they are more or less related to that. Your dual theory will have a black hole, but then you need a dual theory for that. Then you look at this thing and you realize that the theory that we are talking about is not strictly unitary, in the sense that you have picked one j out of a distribution. Each one of the theories that you pick is perfectly defined nice theory, but here what we are doing is that we are picking them at random and then doing a disorder average. And then at least what a little bit that I know about gauge gravity duality is that you need a gauge field to make it work nicely, and here certainly we don't have a gauge field. So maybe if we are interested in black holes, then we should change this model little bit, and this is what is done here by Klebanov, Tarnopolsky, and Witten. Obviously Witten on the first time, but he did not put all these things properly, but then Klebanov. So this is the model we are looking at. This is called tensor model, which has now a gauge field. So this has a gauge field here, and this guy is the interaction strength, which is again some suitable powers of n, and this psi to the q, this is some q vertex interaction, which I will be explaining here.
Yes. What went wrong without the gauge field?
Huh?
You said something is wrong without the gauge field.
So in usual way of the way I know about ADS safety, at least you need a boundary gauge field to make it work. So if you are, so what happens in this duality is that you have a gauge field on the boundary, and then the bulk coupling goes as like 1 by some suitable powers of n, the large n, the gauge field had some parameter, the large n parameter n, and then this goes as 1 by n squared. So if I don't know if there is any method of getting this thing without any gauge field on the boundary, it could be, I don't know.
The global symmetry is not
need some analog of Gauss law condition so that your
singlet you want to get.
so that you have only a small number of measurables. That's how maybe ACFT normally works. Maybe it's something more different. But the thing about ADI-CFT is it's a theory with a very large number of degrees of freedom, and yet the number of low energy observables is finite. Stays finite as that number, very large number goes to it. That's usual.
Yeah, but this property is not there in the normal SYK.
There's no particular reason to restrict it.
There is no gauge field in this thing, you see.
After you're done.
No, please.
No, I've slightly forgotten. So if I just took the SYK model where you had this averaging over the couplings, and I tried to get rid of that feature to get an obviously unitary theory, but I just choose a particular coupling and some, I don't know what it is, Q point interaction in the fermions, which carry various indices. Can I get the same Mellon graphs, or do I mean, what role does if my idea is just to reproduce the Mellon graphs at leading order in n of interest, I mean the gauge field is not propagating, right? So can I do it in that way?
So what happens is that suppose you have two insertions of this vertex, and then because when you do the disorder average, see many of the things are zero, namely if you do the disorder average only, then some certain class of graphs will contribute. So if you don't do the disorder average, then you will get many other graphs which will also contribute, apart from this Melonic.
Is there a variation of the model where, let's say you had like a 3-point interaction or a 4-point, I guess it's a 4-point with some Mellon. Now I have some flow of indices, some tetrahedron kind of vertex. Can I arrange it so that without gauge fields also I reproduce the Mellon graphs?
I don't know.
I think the following is a plausible statement. The question, you could just choose one particular set of J's from the random answer. Some not too untypical set of J's. Let that be all. Then the question is, for suitable observables, does the model self-average?
Right, okay.
If it does, then for those observables, that particular model will also be dominated in large n by these.
Yeah.
By these. So the key there is that for suitable observables.
Okay. Okay, so that's one question you can ask, but I was asking a slightly dumber question, which is, in the end, if you're interested in a set of Melonic graphs, can you, is it essential to, what role is the gauge field playing in Witten in getting the right Mellon graphs? Because the gauge fields are not propagated.
Oh, it's like, no, you could take that to be a global symmetry.
We take it to be a global symmetry. Okay.
And then just by hand restrict to, say, the single.
Oh, okay, that's what I wanted to ask.
Yeah.
So he has, what Witten has is some aquatic interaction, or can be Q point or whatever.
Yes.
And gets the same Mellon graphs. As
Yes, you can set this A to be 0 locally, is A0 to be
That's
0
what I was
locally.
asking. And then if you look at the invariance under the symmetry,
Yeah.
then for the correlators,
Yeah. In fact, Witten does not clearly commit in his paper to whether he gauges the model.
I see, I don't remember exactly. I see.
He leaves it open.
Oh, I see.
And
Yeah.
So leaving out the global symmetry is also good.
Leaving out of your
Just assuming that the boundary theory has a global symmetry without introduction of the gauge symmetry, then you can have it.
you will get a certain set of graphs. You get whether you want to interpret that as a ADI-CFT or not is another. But just for Sandeep's question, it's fine.
And then you said that Witten didn't get something quite right in Klevenov and Tarnopolsky. Again, I don't quite remember that.
I don't know what that statement.
They tried to do it in higher D and this and that, but I didn't think there was anything wrong.
no. By that I don't mean that that was wrong attempt. What I mean is that if you really want to make the statement that I am gauging my theory and writing them in a manner where you have the things that has gauge indices, that explicit thing probably came in this paper by Klevenov. That's all I meant.
I mean, clearly Witten had gauge theory in mind. I don't think that's a fair
He
statement.
does mention
Okay.
it for sure.
Fine. So I am not criticizing
fine,
by.
go ahead. I'm just making sure there was nothing missing in my understanding. Okay, go ahead. Yeah. Okay.
Okay, so this Q vertex, this is drawn for Q equal to 4. Let's look at in one of the places how it looks like the interaction. So any one of them, this color gets contracted with one of the others. So if I write it in index notation, it will be like ABC.
You want to say how many gauge groups there are? People
Yes, I will be saying these things. For q equal to 4, I will make things very clear and precise. So this is the interaction term, at least for q equal to 4, it looks like this, where you see that any one of the colors from this guy goes to exactly one of the others, not two contractions, and this one gets contracted with this one with that one, and same with the other ones. So it's like only one of the colors will get contracted with the other one. You can draw this tetrahedron picture for this thing. So this is the interaction thing. And then if we are talking about q equal to 4 and we have 3 indices, in general if you have q number of fermions interacting, then to make this thing work, this contraction, you need q minus 1 gauge indices. That means, and we particularly choose this gauge group ON, and then we are working with ON to the q minus 1. So each fermion is in one of the fundamentals of ON. So there are q minus 1 different ONs under which this fermion is gauged.
Why do you need q minus 1 for q point vertex? Why do you need q minus 1 colors?
Because you want to get this particular kind of contraction. At least if you have q minus 1 of them, then there is this certain rule with which you can get this interaction. And then about this particular scaling with n. So I am drawing two graphs, one of them this kind of graphs which has, this is the basic interaction term. If you have graphs built out of these things, then these are called Melonic ones. So certainly this is a Melonic one, but this is not. So I will show you in this simple example why these are dominant in large n. So there are two interactions, two vertices. So j by n to the 3 half to the 2 from here, and then number of loops that you have. Each color has 2 loops, and there are 3 colors in it. So you get this is the effective thing that you get, and if you take the free graph, that also has n cube. So this is the, so if you keep this, if you write your interaction term in this form and keep j fixed while you take n goes to infinity, then this graph scales like this. Whereas this is some non-Melonic graph. If you do the same analysis, you get 3 of them, and then you have less number of loops. So this is subdominant in large n limit as compared to these Melonic graphs. And Klebanov has gone to some distance to prove.
Could you just explain in brief what you mean by contraction? I'm just a little confused. If you could just explain what you mean by a contraction.
What do I mean by a contraction? Well, so this whole thing has to be invariant under if you rotate this guy and rotate this guy under, let's say, the first gauge group. So by contraction I mean the combination is such that under this rotation this will not change. Just like usual things. Which vertex?
The A naught psi current vertex that you have.
A naught psi. Oh, which one? Sorry. Oh, we are locally going to set A0 to be 0, and we are going to do all the calculation in this gauge because we are in very low dimensions. Only this holonomies will play a role. So this is the interaction structure, and then we go forward. Now this has nothing like some random average, so it is nice in this sense, and it is shown that this model in large n limit, the leading order at least matches with the corresponding one with SYK. But this model has a gauge field, so it has a Gauss law, some constants that will play a crucial role. And then you write down this action. This action has the property that if you take the classical equations from this action, it will give you some equations, 2 equations for 2 variations, sigma and g, and these equations are the large n effective equations that you get from the Melonic diagrams. So this gives the correct Largen equations.
Just, I mean, in terms of summing, are you just summing repeated insertions of that mel?
Yeah, so you can also have graphs like this.
Or melons upon melons.
Melons upon melons. Thank you.
So the first term comes from coming over those melon diagrams.
Yeah. Which one? So
So Hagedorn is where each of the terms in the effective action comes.
yeah, so if you just vary this thing, let's say with respect to g, then you get sigma is equal to, this is the term that says that sigma is the self energy because of the interactions, and then you have the other equation which is like so this ensures that on the classical trajectory at least this is like the self energy.
And do you want to explain that first equation diagrammatically?
Yes, so this is just that graph. Imagine these things are not joined. Okay. Then this is the interaction that you get from this guy.
See, any self energy is one melon or melons upon melons. But you see, if you think about it, melons upon melons is the same as one melon, but with the exact property. Okay? So sigma is a melon graph with the exact property.
It's like a self-consistent.
Yes.
This is the correct propagator that you want to put.
Yeah.
And then other thing is that if you choose these indices to be diagonal, these indices for both the fields to be diagonal, then this action goes like into the q minus 1 in front, and then this thing. This is exactly the action that you will get for exactly the action that you will get if you take the SYK model with that many degrees of freedom. That is another statement that this action is nice, but we don't have some clear-cut derivation for this action. Okay. Now you go to j equal to infinity limit, drop this kinetic term because it is irrelevant, and then you fix to a particular gauge which is a0 equal to 0 gauge. Now when you have fixed the gauge, you make these time dependent rotations. These are time dependent rotations of the psi fields, which translates to these things. So if you make these time dependent rotations, then the because this term is not there, the action is invariant. But this is not a gauge transformations because we are not changing the gauge, because gauge field does not even enter when you have dropped the kinetic term. So these are not gauge transformations, these are some different rotations, time dependent rotations, which are symmetries of this action. Okay. Now
But the symmetry exists when the gauge field is not into 0. So A0 is also
yes, so
square.
but then you cannot do this time dependent part. If you do the time dependent part, then if the kinetic term is not ignored, then that term you will need to change the gauge field.
Right.
So
That's
only
the usual gauge symmetry.
usual gauge symmetry. So only when this term is dropped, then this is like a symmetry.
Right. So what's being done is you phase the fermion without changing the gauge. This is not a symmetry of the interaction.
And this is
However,
only when we drop
in the
first.
low energy limit, it becomes an effective symmetry.
Just like the one that we had in SYK, that diffeomorphisms was not symmetry when J is some arbitrary thing, but at J equal to infinity you had this symmetry.
So this is not a gauge redundancy, but
No, it's a
actual
genuine
symmetry.
It's a actual symmetry at J equal to infinity. Okay, now this action looks, there are lots of fields, there are these contractions.
I was also going to ask, I'm a bit confused. Sorry to go back. In SYK, if you could drop the kinetic energy term, then you had this exact angle parameterization.
Yes.
Symmetry. That didn't require J equals infinity or anything, right?
So you
Oh,
can-
just you're dropping that
You are
term.
dropping the
Oh,
term
that's
based
what
on
you mean,
this.
that's what- okay, I was thinking you take temperature to go to. Okay. All right. Dimensionless parameter. I see. Okay. And here is the statement that because you had indices actually in the limit where j goes to infinity, or you drop the kinetic energy term, the full symmetry is bigger than just time reparameterization?
Yes, so time reparameterizations are also symmetry in this thing, which I am not. It's bigger than this because the indices can also rotate now.
Much bigger.
Much bigger, much bigger.
Yeah, there are
It's n square, I mean, yeah.
exactly n square number of fields that you are getting for extra.
Okay.
That is very important because we are taking n going to infinity. So this action has lots of fields like the sigma and g. So you have into the 2 into q minus 1 fields, whereas these rotations that we are going to discuss little bit afterwards, they have just order n square fields. Then if you we are going to calculate some effective action for these rotations from this action. So then we will see that at the end the action that we will get, that is actually weakly coupled. Now you had this symmetry on the last page. Now if you take these diagonal solutions where I am using the function is just syk and then the diagonal things, then that solution is a solution of this index with index equation, but if you make some arbitrary rotation, time dependent rotation, then these solutions will change. So again we are getting that this classical solution is breaking that time dependent part, but the time independent part is still there.
And it will change it because j is not strictly.
Yeah. So it will again if we try to calculate the effective action at strictly j equal to infinity, we will get nothing. But when we go, we will break that little bit in 1 by j order, we will get something for these modes. The similar story as with syk.
Sorry, but if I looked at it at j equal to infinity and I looked at your solution, do you break this rotational symmetry?
Yes, I break the symmetry. I break it.
Even at j equals infinity?
Even at j equal to infinity. But I don't get anything for that.
You get, I understand.
Manifold of massless.
Yes.
Singular. Massless.
A mass.
Quote unquote zero modes because it's all time, etc. I got it. Yeah.
Okay, now we are going to calculate some effective action for these V fields that I have written down. That we do by expanding this field G and sigma around the classical solution. Currently I am not assuming that these are the conformal solutions. I am assuming these are some classical solutions of the gap equations, and I am expanding them. This G, small g is the fluctuation of 2-point function, and this is the fluctuation of self energy in this notation, and I am scaling them properly to make some calculational simplicity. We could have done this thing without scaling, but it would have been complicated. And then we substitute them back in the action that we had, and then we work up to quadratic order in these fields, and then we integrate out one of the fields. We have integrated out sigma in the favor of g. So once you have done this thing, you end up with some action of this form. The action has this structure g k inverse g and gg. This is some kernel. That kernel is completely determined once you know the background solution.
But the kernel carries color indices?
No. This is just a function here, because I am assuming the background solution is diagonal.
Oh,
Whatever that is, but this is diagonal. So
Okay,
they
so-
are in this form.
Oh, I see. Okay.
This is the reason it does not carry anything. And
Probably the gap equation at least gives you that. It might give you more, I don't know.
it might.
It might. This is at least one concept.
Yeah.
These are the things that we are considering. Maybe something better can be done.
Sure.
And then here there are colored indices I have not written. These are pretty complicated contraction that you get from this g to the q term, because g to the q term has some complicated contraction as I have explained. So because that is there. Then if you take this background solution to be j equal to infinity solution, which is a conformal solution, then if you plug that back in, this becomes conformal, and then if you go to some particular class of fluctuations which are the rotations of conformal solution. So at j equal to infinity you had these conformal solutions, then you are rotating them with this v, you will get some change which I am treating as fluctuations. So for this particular class of fluctuations, if you evaluate the action in conformal limit, you will just get a 0. Where h is this, so my v is like 1 plus h. I am taking some infinitesimal transformation, infinitesimal rotation. And the structure of the action is of the following form. So minus structure of the action is of this form, where this is the two g's from two sides, this is the kernel, and this is some from the contraction, some complicated Kronecker delta stuff. Then what we are seeing that this thing, when I am evaluating, this is the fluctuation of conformal solution, this thing is completely 0.
What is completely 0?
So this is the structure of the action that we have, g from both sides and this kernel sitting inside. Now if I evaluate this thing for fluctuations of the conformal solution, and my background solution is j equal to infinity solution, I get 0, the action is 0.
I'm a bit confused about that, sorry. This Kc part is arising because of the kinetic energy term, right?
Yes.
Kc is independent.
Sorry, kinetic energy term you have forgotten, you have removed it.
Forgotten. I see.
K is Kc plus correction. At the moment, he's just saying, suppose you forget about the kinetic energy term.
Oh,
It's just a
then
reiteration
of
in
course,
equations of that.
then of course it will vanish. Yeah. I thought you.
So kinetic term I have dropped completely.
All right. Yeah. Okay. Fine.
And then I am substituting back and integrating. Okay, so we need to go little bit away from conformal limit to get the first non-zero action.
And that will know about it.
That will know about the del t. Now we do this by expanding this kernel around this conformal solution, and then the things that we should, the action that we should get is because of del t, as Cyril said, and that del t is a local quantity. And further we should expect that the global rotations, that the time independent rotations that we can do, these rotations will still remain the symmetry of that action, and we are considering lowest number of derivatives. So that more or less, so if you keep these two rotations as your global symmetry, lowest number of derivatives and a local action, that is the sigma model action. So that is the expectation that you can have even without going with this calculation.
And just to say that again 1 second, so that you have this thing which with no symmetry, with no action, when you drop the derivative. Now the derivative is an irrelevant operator in this thing. So you would expect that it breaks the symmetry, but only in the loop, and therefore gives you a local. The full structure is highly non-local, but you might expect that this in an expansion would give you a local action. However, from equations, that's far from obvious to start with. But that's the general expectation, and then you check.
So we spent some weeks over this, because this is very tricky. There are various sort of divergences that you will face while doing the calculation. Okay, let's not go in this direction, but in Maldas and Stanford something beautiful happens.
Yeah, it felt like a clear argument, but it took a long time to put that argument into equations. It's true.
Sorry, but okay. Then we end up getting this action, where this thing sits in front, and there is one trace inside. So overall into the q minus 1, things are nice. And these are the infinitesimal rotations that you did, and the derivative is from 0 to infinity. Now if you look at the n equal to 0 term, this is just total derivative because there is no derivative here. You ignore that. And then then you notice that the coefficient that is sitting in front is determined by UV properties, some integration of a Dirac delta. So all this calculation is done under the assumption that my j is the largest number, j is going to infinity, and I am going to do things in this expansion. So we are assuming that in all calculation we assume this fact that time differences are much greater than 1 by j. So then you don't expect to get some correct result for C if you put those results. So if you put GC as it was and you do this integration formally, you don't get you get something like 0 you will get. But this is not the correct thing to do, because you are getting the result from something which cares about very short distance properties. So this thing that we have written Cn is like phenomenological for us. We don't know what is that particular value is, but the structure that we got, it came from some calculation which satisfies this constraint. That so the structure remains to be the correct thing, but if this then we will restrict to the lowest number of derivatives, lowest non-trivial number of derivatives, which is one derivative on both of them. If the thing that sits in front is, if the constant that sits in front is not miracle is 0, then to the leading order we get the sigma model action.
So, I mean, what you did was you had that on-shell action in terms of the self-energy and so on.
On-shell action?
Into that you substituted this solution, right? But I'm just wondering, I mean, in turn we had got that on-shell action in terms of the self-energy by first starting with psi, dt psi, and then doing whatever it's called, you know, writing psi as sigma. We can start from the underlying action and then write sigma, the self-energy in terms of the fermionic fields, and do the manipulations to get that starting point, right? Whatever it's called, I forget that name. Yeah, so Schwarzian was some action where something transform or whatever. But would it have been easier to invert it and go back in terms of size or something? I mean, in terms of the size, it seems, I don't know why I say that, but it seems sort of manifestly local in time and so on. I don't know. I mean,
We were integrating out lots of stuff.
you're integrating out lots of stuff, so you may not be able to go back.
Yeah, you may not, it's not so clear that but it's, maybe it is.
I'm just saying the starting point, they seem to be kind of clear that the terms you're ignoring are local in time. But by the time you wrote in terms of sigma and all.
Yeah, right.
Okay.
Maybe it is. Yeah. It's certainly true that it's local.
So this infinite number of derivatives came precisely because of some.
Just let me say the last part. I'll just to make sure people understand this. You see, in solving the gap equation, what people like Malus and Stanford and others are able to do is to solve the equation at long distances compared to G. Okay. Now we find the structure of the action reliably, and then there's an expression for the coefficient which involves involves integrations over the whole solution, and receives important contributions from the regions where distances are of order j. So since we don't know the exact solution there, we cannot get the exact number. But you can estimate orders of magnitude because you know the width of that solution. So you can get the coefficients of this up to unknown numbers of order 1. Okay? And we're assuming that unknown number of order 1 is not 0 for some strange reason. That is a major. That's it.
And this to get this number straight, probably a 4-point function calculation from the other end could help, because they will get significant contributions from these things, just like the Schwarzians did.
From the other end meaning?
Okay, so you can calculate this out of time ordered 4-point correlator, and in SOIK you get this exponential growth, and that exponential growth precisely came from the contribution of Schwarzians. precisely from these diffeomorphisms. So in this case, if we do the same calculation in this model, then these 0 modes will also contribute on this out of time ordered 4-point functions.
That's a relatively trivial calculation.
Yeah, Klebanov is actually done.
I mean, okay, clever, but I mean, you just need to know the dimensions of the fields and you can couple it to the time reparameterization mode and then integrate out. I mean, I'm not sure I understand what. So that's a very trivial
That's a very
thing to.
And then you want to compare it with an exact answer. And that should give you an answer for this coupling. Klebanov and company have done the exact calculation. So just by solving the Stringer-Dyson equation for the 4-point function, have computed psi. Okay? And they do see the kind of behavior you would expect if you had an intermediate something like this running. Comparing, we could pull out that number.
We have not done some careful thing to get this number out from their paper.
I mean, they did that. Their paper was simultaneous.
Simultaneous with it, so did not get the time. But important difference is that now you have lots of these modes, so there are so many factors of n sitting in front. So when you will do this calculation in the correlators, these modes will at least dominate the physics for times of the order 1 by temperature times log n. So there is this exponential contribution from the Schwarzians, and then you have things like this from our modes. There is one n square sitting in front. So this thing will dominate for time scales of the order . So after this time scale, if you go to further, then you will probably get this dominant contribution from the diffeomorphisms.
Did you mention that f of t was power law in our situation?
Yes. So in our case, so the thing is that in our case, the action in momentum space is just like this, and that does not give you any exponential growth, like the Schwarzian. So Schwarzians, even if you look at the classical equations that you get from the Schwarzian action, and if you try to solve them, then you will see that you will get exponential growths. But in our case, it will.
Sorry, what are you computing now?
We are computing this thing, correlator, which is you have
Okay, 4 points.
yes, and yes, and that is given by some. Let me illustrate the calculation in SYK, that will tell us what is required. So it is roughly given by this, where 2 insertions of G and integration with respect to the action, which will become e to the diffeomorphism action, the action you get from diffeomorphisms, and then 2 factors of, let us say epsilon is the infinitesimal diffeomorphism, then this thing is where n is the Fourier expansion of this infinitesimal diffeomorphism. So I have taken some arbitrary diffeomorphism and Fourier expanded into modes. This n characterizes this mode number, and then so this 4-point function is basically something like this. Now because of the Schwarzian, now this details of this action plays a role, because this thing in terms of these coordinates has the following structure. So the thing that you will get from here is this. If you make the inverse Fourier transformation, then you get something like sin t, sin tau is the imaginary time, along with power laws. So that grows exponentially in time, real time. And then there is some details about this correlator with which you do some calculations and you get exponential growth of this, the exponential growth I talked about, that saturates the chaos bound. Now imagine we are doing the same computation with our modes. Now our action is not like this, our action is just like, it has just this thing, it does not have that guy. So if you make inverse Fourier transformation of this guy, you just get power laws. So our contribution is like n square times some power law, whereas their contribution is like 1 times some exponential. So for small times our modes dominate, but we don't have some exponential growth. Now all this calculation is done in the gauge where we have set A0 equal to 0.
I'm just sorry, confused. Psi is your elementary field, so it carries color indices?
Yeah. So we could do it with any object.
I mean, I'm just, you could do it with the gauge and
Yeah, you could do it.
Because of this butterfly stuff.
In fact, you couldn't do it with psi bar psi because that would be neutral under argument because those are equal times. But psi bar del t psi, anything that is the charged under argument. The details don't matter because you see, basically you're kicking the field and then it's growing in time and then you're measuring it. The exponential growth or the growth in time is how the intermediate guy grows in time. So the important thing is that the Schwarzian itself had a growth that was exponential. You take the Schwarzian action, you move to a Lorentzian time, there is one mode that grows exponentially. That gives rise to the chaos. Okay? In our case, because it's just a sigma model, things grow in time that have at most power. Anything that kicks it will grow.
Why does it even grow?
Why does it grow? It's because let's take
you're in 0 plus 1, you said?
yeah, let's take a U1 theory. The equation is del t squared of phi is equal to 0, so there's a linear growth.
In hierarchy, the Green's functions would have fallen back in the
Yeah.
Now you can turn on holonomies for these gauge fields, which is equivalent to putting suitable boundary conditions on fermionic fields, and that translates to this thing. This translates to this boundary condition for this V. L is the color index, color group you are talking about. L goes from 1 to q minus 1. Now if you plan to calculate the partition function of this part of the action with this kind of boundary conditions, that is equivalent to calculating trace of this quantity, where this is the usual thing and this is that takes care of the boundary condition. Now that thing is some group theory calculation that we did, that you can do, but before doing this thing, if you just take this thing and integrate with Haar measure on both sides, then the only thing that will click is the trivial representation, and you will get 1 from this. So the partition function that you get from these modes, if there is no other contribution to holonomy apart from this thing, then the partition function is just trivial, you can ignore it. But imagine there will be other contributions like fermions coupled to this thing, they can contribute. So if these things also contribute and then you calculate the partition function of holonomies, that could be non-trivial.
So then just the holonomy itself doesn't change the partition function, does it? Because it's a trace or
It's a sigma model over the group manifold. Sigma model over the group manifold has various non-trivial representations of the group, as you know very well. And so if you count only singlets, you don't count. They count 0. But then if you couple them to other things, the other non-trivial representations can couple with the other things to make singlets.
Yes. Otherwise you will just get the vacuum and get 1 if you don't couple other things.
You get many low-lying modes which are all charged under the gauge group. So by themselves they don't contribute much to the partition function, but in combination with other things they can help screen the charges.
Now we are mass deforming our theory. We are working on the limit where J by M is 0. Now we are going to talk about free theory, completely free theory. Our mass is there. So we have introduced mass in our theory, but we are talking about free theory. Then you can integrate out these massive fermions and with the holonomy. So we are putting the holonomy inside, and we are doing the path integral to calculate the partition function for the holonomies by integrating out the free fermions, and you end up getting some result like this, where
Can I ask you just a basic question before we go there, which is when you first introduced the SYK model, you said just because in Euclidean time the 2-point correlator had some sign behavior, then it became sign hyperbolic maybe in the denominator, so it's self-averaged or it's thermalized.
thermalizes, yes.
And here the large number of modes, do they come in the way of that thermalization or do they aid it? Does it even thermalize? It probably does at very long time. So.
I cannot answer.
The basic 2-point function of the fermions is the same.
It's the same.
In j going to infinity limit.
Right.
That was just a j going to infinity. Yeah, that was just from your Green's function.
Right.
Which was calculated at j equal to infinity for SYK even.
Okay, that is the same.
Yeah.
That is the same.
So some of these guys are not harming that.
Yeah. It's like, yeah.
I see.
Yeah, but what about these ones? Yeah, that's an interesting.
Maybe for the same reason you're saying they don't quite enter in the partition function as such. If I understand.
Just by themselves they don't enter.
Singlet sector.
It is interesting though, because it sounds like there's an effectively integrable, sigma models are integrable, they're not really fundamental. It does sound like there should be some sector of the model that does not. That sounds right. That sounds right. It's from the point of view of the bulk, these are probably gauge fields in the bulk. And they should easily. I think that sounds right. Meaning that it's almost like there is an let's take the ungauged model for a minute.
I mean, sorry, just to say one thing, but what I thought you would tell me is that no, that SYK calculation was for some singlet kind of 2-point correlator. That is, if you kept your color indices in some way, then those correlators would behave differently. That's not the case.
No, I think even, yeah. See, I'm not sure, but I think if you see the 4-point function of these guys, the kind of correlator we would have to look at would be like a gauge invariant. So it would be a 2-point function of the kind of thing that these guys do with 4-point function.
Yeah, that's right. I think that's right.
And certainly the out-of-time ordered guys, so whether you get something interesting without out-of-time ordering is your question. I mean, not 100% sure. In a way, these guys didn't get anything interesting with the Schwarzian, so why should we?
And they didn't get anything interesting, but they probably got, I don't know, just the 4 size probably factorized into 2 size, each of which dies exponentially fast.
I suppose. Yeah, I suppose that's somehow what's going on. I suspect that whatever happens with the Schwarzian will happen with our situation. So I suspect that this growth in time needs out of time.
It will thermalize.
In terms of 2-point functions will just thermalize. Because it just seems like the calculation will be more or less the same as the Schwarzian. And that's what happened in there. But I haven't heard it.
Okay, so now we are talking about mass deformed theory, in which we are working in a limit where j equal to 0, j by m equal to 0, and we are integrating out the massive fermions. Then we are getting some effective action for the holonomies. Now this is the effective action for the holonomies, where this rho this is the eigenvalue density function for the holonomy matrices, and this first term, this n square times this thing, this comes just from the Haar measure of the gauge group, and then this is the term that comes from the fermion. So the part that comes from the gauge group is just independent of temperature, it is just the measure of the gauge group, but the term that comes from the fermions knows about the temperature. Here the x that I am writing out, x is just e to the minus m beta. So if temperature increases, x increases, but there is a relative factor of n sitting in between. The Haar measure is of the order n square, whereas this fermion contribution that we get is of the order n to the q minus 1 because of so many degrees of freedom. But so they do not really interact if they are of this order. If x is of the order 1, then they do not really interact. But then we can get into interesting dynamics by saying that, okay, let's look at x to be very small, namely scale x to be like this, where alpha is kept fixed, p is some number, and so x goes like 1 by n to the q minus 3 and n to the q minus 1 sitting upstairs. So you will get even the fermion part in this limit becomes of the order n square. So then they two can interact. Now important part is this, that if you have just this part in the action, then what this part tries to do is to make all of them 0, which means that it tries to make the eigenvalue distribution uniform on the circle. We are working on ON. So on the circle they try to make everything uniform, whereas this fermion part, it can be proved after small calculation that they try to make peak distribution, like peaked somewhere. So they are opposite. So definitely in this limit we expect something non-trivial going on, some interplay between these two things. And in this limit you can also drop higher powers of x because they are subdominant compared to these things. This I will be calling as the scaling limit. So now we will be studying this action and try to calculate some thermodynamics.
Sorry, with the fact that this is the correct scaling, is that supposed to be obvious from everything you just said?
Yes, because this,
I didn't understand.
yes, so the contribution that you get from the gauge group, the Haar measure part, that simply goes like n square because you have ON groups.
That I understand.
Now then from the fermion part, even you want to scale x such that that is also order n square.
That's all right. Okay, that's how you get your n to the q.
Yes,
Okay.
and the number.
The reason I'm a bit confused, I see, you're only keeping the first term, n equal.
Yeah, all the others go to
Right,
zero.
right. I see.
Sorry.
Sorry. And so you're working with. Okay, I see. All right, thank you. Okay, go ahead. Yeah.
You do the scaling and then you have to
Okay.
draw.
Yeah. Thank you.
Also simplifies it.
Yeah. Okay.
So we will be studying this action in this particular limit that I talked about. And then we try to evaluate the partition function, but we use saddle point analysis, and then after some variable change that can be mapped with this Gauss-Witten-Wadia kind of model for unitary theories, and then you do some algebra and you find this, that on the saddle point this the color index which goes from 1 to q minus 1, different colors, and 1 is just because we kept the x to the 1. So this thing for all the colors are the same, which I am writing as u. All of them are same on the saddle point, and then you substitute back in the partition function and you get the partition function of this form, where vu is this function. The u to the q minus 1 came from this product. You had this q minus 1 fermions, that thing, and where this f of u is given as a function of u for u less than equal to half, less than equal to half by just simply u squared, which I will be calling as OAB phase. The OAB phase is the easy phase, and then the other one I will be calling as the gapped phase. So if I give you some particular temperature, so temperature is like alpha in my thing because x is scaled by alpha by n to the q minus 3. So if temperature goes up, alpha goes up. So if I give you some particular value of alpha and ask you to calculate the partition function, you first plot this function v of u and find its extremum points. Find where it is minimum or maximum, and then you choose the suitable point to get the action.
So can I just ask something? You might be coming to that. If you can just go to the previous transparency. This row of n is the nth moment, is that right?
Yes, it's the nth moment of mth color group.
MF, but okay. Everything is M neutral, right? Basically in your saddle point.
Yes.
And then the whole story of the phase transition is that the full row after summing over all nodes has to be positive everywhere, right? So that's what you're going to now investigate, is it? Where you can get a solution. I mean, to begin with, if you neglect that term, it's totally uniform with row 1 presumably 0, is that right?
Yeah.
Yeah, because just from the saddle point. And then you pick up some small row 1,
Yes.
and then at some point row becomes, okay.
Okay.
Just want to
And you know, the one new element is that there's an interesting nonlinear potential. You see,
which couples the different ends.
which couples the different gauge groups. Yes. So because the holonomy for each gauge group is independent. Let's say we are restricted to n equals 1. So we've got row. So I'm not even going to say the n index. So we've got row 1, row 2, row 3, and so on.
Right.
When we vary with respect to row 1, we get the product row 2, row 3, row 4, and so on.
Yeah.
However, you can prove that all solutions of these preserve the replica symmetry. So row 1 is equal to row 2 is equal to row 3. So you get a term in the potential that is rho to the power
Q minus 1.
Q minus 1.
Right.
So although you get a Grossman-Wadia type equation, it's for an effective coupling constant which itself is rho to the power Q minus 1. So you get slightly more interesting dynamic behavior than Grossman-Wadia.
Okay, so here I am plotting few graphs for different values of alpha. So there are few particular choices for alpha, namely alpha c that I will be talking about. They are determined, like alpha c is something like 2 to the q minus 1 or something. They're determined. So when we are below this alpha c, then the potential just looks like this, where we have only one extrema at the origin, which is this way I am plotting u. So at u equal to 0. And then if you increase alpha and make it equal to alpha c, then you will get a point of inflation at some value which is above u equal to half. U equal to half was the boundary between gapped phase and the wavy phase. So when this inflation develops, it is on the gapped phase. And then you keep increasing this value of alpha, and the minima that gets developed keeps going on higher values of u, and the maxima that keeps going on the lower values of u. So the minima goes like this, and the maxima goes like this. And then at alpha equal to alpha pt, this is wrong, at alpha equal to alpha pt some particular value, you see that this maximum comes from this gapped phase and goes to the wavy phase, it moves. And then if you keep increasing that value of alpha, then eventually the minima that there was, that come to this point, which is the same as the minima of u equal to 0. So beyond that, if you increase alpha, then the dominant saddle will become this one. Before that, in all the pictures, the dominant was.
Before that, it's the wavy.
Yes.
It's beautiful.
Oh, is it identical?
Because it's sitting at u equals 0.
Achha. It doesn't require even a small wave.
Not in saddle.
And then
There's a maximum that does all this, but that's like a small value. It's not relevant.
and this is like the black hole saddle point, and in the dual picture this is the deconfined phase. So at this alpha equal to alpha 1 pt, this thing goes a first order jump, where the saddle point from here to becomes there. This is the Hawking phase transition we expect, because you are increasing the temperature, you are increasing alpha, and you are getting the first order jump.
So even though we use a Gross-Witten quadratic to solve this, the final physics is quite different from those. The first order and the third order.
Third order phase transition will be somewhere else in this. Then so this is the story as a function of alpha, means the temperature. So you increase the temperature beyond some point, you make a first order transition to the black hole saddle point. And now we are doing some microcanonical analysis where as a function of energy we compute the density of states. Now it is the first thing that we do is to try to calculate around the trivial saddle point at u equal to 0, and at this point all the partition function is just 0, and energy and entropy all of them are 0. Then you say,
Sorry, you just remind me again, what was u again? Sorry, just for 1 second.
so the partition function is written in terms of
u, which is rho 1 of n. Okay, got it.
Now if you calculate everything for u equal to 0, this is the trivial saddle, then you get energy and entropy all of them are 0.
So the saddle point value is trivial, but you can do the one loop around.
Yes, so now we are going to do the one loop analysis around the saddle point, in which case we did not restrict to the fact that we are taking only linear term in x. There was this power of x higher power, so for this small analysis we keep all the powers of x as well.
Just because we can. For this trivial saddle point, you can solve the fluctuations more generally.
And then for every, so if we go back to this action, then for every value of n equal to 1 to infinity, for every value of n, the partition function gets a contribution like this function fn, which I am calling some function fn. So for given value of n, you can do this integration through Wick's theorem. Although this is divergent.
Is that right? I mean, I know you guys are very strong, but sorry, isn't this some pretty non-linear? You guys are made of obviously Stirner stuff done. Is that right? I see. It's not entirely obvious.
You just bring down as many powers as you want
Bring down as many powers.
and contract.
I see.
That's the Wick's theorem that you
And it's
do.
so simple because it's 0 dimension. It's just a counting problem, how many contractions.
But you're not doing it in perturbation theory X, because you said you're doing exact. You want to, let me just make sure that you want to do the partition function, so you really want to do the integral. And it's some pretty non-linear integral.
No, so at order by order in x, you
Order by order in X. Okay, fine.
For every-
No, I'm with you.
Yes.
Order by order in X.
do for qth order, for arbitrary q, you define the coefficient.
For arbitrary Q is the gauge group.
No, sorry, q is I said for alpha, any. For at a millionth order, you define the coefficient
In X.
in x.
Yes.
Okay.
That's
Okay. All right.
Then it's some. Yeah.
I see.
So for a given value of n, you do this integration, and as a power of x, you get quantities like this, x to the some power times some number, and then you identify this thing as some system. X is like e to the minus m beta. Yes. So you identify this thing and you get the yes. So you get the density of states.
Yeah. In order to read out the density of states, you don't need the exact answer. You actually need the coefficient of x to something, because that's the entropy.
Yeah. So this gives the density of states. The thing that multiplies x, this thing when
You get an
written.
exact expression for rho of e.
So for every given value of n, you get some effective entropy, which is given by this formula, written in terms of energy.
Can I ask you something dumb when it's not related to what you're doing just now, and we can talk about it later, but Witten with Stanford wrote this paper where they computed the partition, they did the whatever Schwarzian integral exactly using whatever some localization technique and so on. They got an answer and they said it can't arise from any principle theory, etc., etc. And does that story change with your n fields and so on?
You're saying if you add the action of the Schwarzian to the action of this thing?
Yeah.
I don't think so, because the partition function of the n fields itself can arise from unitary, because it's just quantization of sigma. The big difference is that the Schwarzian was non-compact, whereas our sigma model is compact. So will be a product of two things, one of which can and one of which cannot.
So it's just a product. Those modes are different from these.
Yeah.
There's no interaction.
As far as we can tell, I mean, it could be that we missed some interesting zero points. You know, we just observed that this is an interesting zero point sector. We've not proved that there are no other interesting zero points. So it is always possible that there is a larger story than what we have, which can put things together in a more non-trivial way. It's a bit unsatisfying, but it's like there's no interaction between the Schwarzian.
And this.
Yeah, that's what I was.
Probably this is the leading order feature.
Right?
We are just calculating everything at the quadratic order.
I think Sandeep was asking if we just keep forgetting about this mass definition. You go back to the earlier thing?
Yes, I understood that if you just take the Schwarzian action and our action and you try to do this Witten's analysis.
Right. Right. So if you just take your action to be Schwarzian plus ours, these are uncoupled.
So you get product.
You get a product. Yeah. However, if there were more interesting low energy modes that somehow mixed, wasn't just like then maybe something interesting.
Are you trying to look at a Schwarzian for every in degree of freedom?
The kind of thing we tried, we never managed to make sense of. We thought maybe there's something more interesting. We never managed to find another zero. But it's we didn't prove that there isn't. It's possible.
Actually, now that I say it, I don't even quite recall properly what Witten was saying. I mean, if you take his theory or whatever, it's clearly a sensible theory to begin with, right?
Oh, it's not so clear. Okay, yeah.
Is it a comment on the large n limit?
Oh, no. Yeah, he's just taking the theory defined purely by the Schwarzian.
Right. But what I was saying was that there is an underlying theory which he writes down, unitary, everything.
Yes.
And this Schwarzian is arising as the low energy sector there,
But you know,
with your extra stuff perhaps.
and with the saddle point. You know, the full free energy is that the saddle point value times the Schwarzian value.
Times the Schwarzian.
And the saddle point is like n squared dominant compared to the Schwarzian. So what you're doing is take a first correction and ask, can you regard that as a consistent partition function for an autonomous system?
No, okay, but what I was trying to ask was exactly that. That suppose I had not done that, I take the full answer I get in this theory.
Yeah.
Maybe in large n.
Yes.
But I get something.
Yeah.
Then I ask, can that arise? I mean, so what is
That's
curing
the
the pathology he found? Again, this is more that I do. There was some pathology he found from just the Schwarzian piece. If you just, because the added part is just some zero temperature degeneracy, right? In the partition.
No,
function.
also some linear specific heat and so on. The added part from the saddle point?
From the saddle point.
No, non-trivial stuff.
Is that right?
Yes.
There is a 1 by beta term in entropy from the saddle point, which is like linear.
Yeah. Quite non-trivial stuff.
I get confused because, okay, well, we should have some proper discussion because, alright, Jacob Teitelbaum, anyway, alright, okay. We got to settle various things. Alright, I see. So there's additional stuff. So if you keep the additional stuff,
Yeah, then there's no issue.
so then it's a bit of a red herring, right?
Yeah,
This is
then why
kind
should
of
you have?
Yeah, I mean, then forget it. I mean, why are you
It's
just.
a purely mathematician's question.
But in Jacob Teitelbaum, I don't know. Okay, well, let's just check because there I thought the full finite temperature, low temperature contribution is the Schwarzian contribution. What's the extra stuff?
Whatever you get from gravity. I mean, black hole entropy. There's no such thing as black hole entropy in black hole.
No, the action is phi r minus lambda is not the r is lambda.
And there's no black hole entropy.
There might be ground state degeneracy, but that's it. No temperature contribution. as far as I know. But
Yeah.
the various things. Okay. All right. Okay. Okay. Please. Sorry. Go ahead. So
Okay.
then for this model, those kind of comments are just answer that.
Yeah.
Okay. Fine.
Okay, so we computed now that if you want the dominant answer, then you choose n equal to 1, that gives the maximum entropy. But this calculation is done around the saddle point at u equal to 0, and we did this one loop calculation to get this entropy. But then we did some different calculation, which is the calculation around the saddle point of OAB phase. Suppose your maxima is somewhere here, and you are calculating the contribution from this thing, OAB phase, and then you calculate the entropy in the saddle point, and surprisingly that becomes the same result. So one calculation is around u equal to 0 saddle point, in which you calculated one loop entropy, and other one is around some saddle point in OAB phase, and you are getting the same result as for the entropy.
A bit confused. Sorry. I thought what you were getting. What is the wavy phase again? I thought there's a first order transition. U1 is 0, and then it jumps discontinuously. What's the wavy phase discontinuously?
So the OAB phase is the one in which the graph in which this part is the OAB phase. The jump happens in the gapped phase. So you had this u at 0 here, and the jump happens to the gapped phase. OAB phase is this part.
Exactly. Yeah. The relevant thing is the top part, the maximum.
What's being plotted? V of u, right?
Yeah.
Yes.
So you see there are two different things. There's a question of which phases ever are matter for the canonical ensemble, and which phases ever matter for the microcanonical.
Okay.
And it can happen that a phase never dominates the canonical ensemble, but gives you the leading behavior for the microcanonical.
Is that right?
Yes. So for small black holes in ADS-CFT, for instance, that's what. So for instance, in the Hawking-Page transition, canonical ensemble is a jump from a state that has energy order 1 to a state that has energy order some critical value times n square. So what happens in between those energies? Between 1 and that, let's say, pi times n square, the canonical ensemble never gives you a phase between that. But you can ask, what is the density of states?
I see.
Okay?
If I was strings or something.
It's strings if it's order 1, but then
Oh,
small
that's
black
it.
holes if it's order n square but lower than that pi. So it's a similar kind of question that Indranil is asking now. What happens as a function of energy? For this question of saddle points that never dominate the canonical ensemble could prove crucial.
I see. So it's those top.
Those top things.
Got you.
It's like the small black hole.
Okay. Interesting. All right.
So this one loop calculation is here, and this saddle point calculation is here,
Okay, I got it. I see.
and we get the same result.
So the one loop calculation is relevant for energies large compared to 1. I mean, you get the same result as E much greater than 1 in the.
Yes, so this result is valid for energies much greater than 1, but much less than n squared. This is the calculation, this one loop calculation, and then you calculate the entropy from this guy, the maximum, and you also get the same contribution, which is again valid from 1 to n squared by 4 of the order n squared, this thing.
So the second one is valid for alpha times n squared. So you would expect that if you took E much greater than 1, and E is alpha times n squared, then E much greater than 1 matches with the small alpha limit of the other thing, and that works very nicely. We're pretty sure that's okay. This is continuous, so this behavior continues up to our energies of order n squared by 4, even though the saddle point analysis was, the fluctuation analysis wasn't valid for that. The saddle point takes over and gives you the same analytic behavior.
I see.
And then if you go to energies much greater than n square, at these energies, this only if we calculate entropy from this other minimum, then you get some entropy which just looks like nf times n to the q minus 1 free harmonic oscillators. So in this case, the measured part does not play even a role when energy is much greater than n square, because n squared was the scale for the measured part. So you just get free harmonic oscillators. Now you can ask this question that because if you increase alpha, this maximum was here, and then you increased alpha and it went from the gapped phase to the wavy phase. So you can ask what happens when it is very close to these things. Does the entropy of these two different phases match smoothly? And if you do this calculation, then it happens that entropy as a function of energy goes a third order jump when this saddle goes from gapped phase to wavy phase. So this is the gross Witten-Wadia transition that happens at energy n square by 4.
Why is it third order then? It's a different question. Okay.
That transition.
This is faster than exponential growth.
Yeah, I need to emphasize this very important point that, okay, so at very low energies, like energies less than n square by 4, this energies, this thing, if you look at it, it's higher than, the density of states is higher than e to the e, it's e to the log e. So if you, whatever the dual of these modes will be in the bulk, the density of states is very large as compared to e to the e. So at a given temperature, they probably cannot thermalize with normal e to the.
Why is it Sn? We are looking at Sn, right?
I am talking about density of states.
Density of states. Okay, e to the Sn. Let's say that's the number of states.
No, but Sn goes like e. Yeah, right. Yeah.
Yes.
Sn goes like e to the power Sn goes like e to the power e log.
Okay. So, but here
That's e factorial.
The
Exclamation mark is factorial.
This is e log e
That's it.
in exponential.
I see.
So they have very large density of states as a function of energy. So with the matters which are like, which has density of states like e to the e, you cannot thermally be in equilibrium with those kind of matters. So this is probably not a very good thing anyway.
So much faster than e to the e is. So let's see. Normally Hagedorn is e to the e with some coefficient. This is much faster than that. And so nothing like a string phase.
Looks like. If you think about it, every way you think about it looks totally weird.
Now in the mass deformed theory, we are turning on the interaction. We are turning on the interactions, and we are going to calculate the correction to the free energy and the correction to this thermodynamics. So our J by M is still kept very small as compared to 1, and then we do all the Feynman graph calculation in which these Melonic diagrams contribute, and we notice some interesting fact about it, which is that the diagrams which contribute the largest in this limit, where J square beta by M is kept fixed, are this kind of diagrams where all the melons are on a circle. There are other diagrams like melons over melons. This kind of graphs do not contribute to the leading order, because if we look at the propagator here, this is the free propagator, then it has this term which goes forward in time, namely contributes only when t greater than 0, and this is only when t less than 0. But there is an extra factor of x sitting over here when you are going in the opposite direction. So and in our case, x, which is e to the minus m beta, is scaled like 1 by n to the q minus 3. So m beta is like log n. So the more power of beta you will get, the diagram will dominate. So the diagram will dominate. Then we will search for the diagrams which contributes the largest power of beta. Then if we look at diagrams like this, then these things which I call blobs, they have q minus 1 propagators running in between. This is for q equal to 4. Now in any of the propagators you have this factor e to the minus m times t. So if you have q minus 1 factors for each one of the blobs. So if you go forward more with these blobs like t of the order beta with these blobs, then they give very large powers of x, because x is e to the minus m beta. So you do not go large times with these blobs, you go large times only with the external propagators, these propagators. And then I am telling some particular configuration in which all the external propagators are going forward in time, and these blobs are going times very small, so I am just considering blobs are fixed at some points. So this is effectively, blobs are like points, they are not separated much in the times, and all the external propagators are going forward in time. If all of them go forward in time, then you should have one factor of winding. All the times add up and gives one factor of winding, which is e to the minus m beta. Mt and all t sum up to beta, so which is a power of x. But then you have the position of the blobs free. You can go that much with this propagator, or you can go this much with the propagator. As long as you are completing the whole circle, you have these things free. So the integration, so rotation of these things, like the integration over position of these variables, will give you beta to the n, where there are n number of melons on this circle.
You know, I have to say this really does remind me of heavy quark effective field theory. Because the idea is you have a huge, very massive quark or whatever, right, propagating. It's going to interact with your soft stuff, but the soft stuff doesn't prevent it from going along. You know, this is what it seems. So basically it goes along, but it interacts with that stuff, right? And seems like that. This is your quark going around, or it's just being dressed up.
Small dressing, yes.
You can't make pair production or anything. You
Ah.
can't make it go back.
Yeah,
That's
yeah,
like
yeah.
too much.
In fact, basically, there are such low energies
Yeah.
that maybe these effective quarks are not relativistic.
Yeah. No. So that's what I think
Yeah.
is just go along. You never pair
Yeah.
produce a dress. And
Yeah.
this is exactly.
Yeah.
Yeah. Okay. Great.
Okay, so this kind of diagrams, when all of them goes forward, that gives the beta to the power n, which is the maximum that you can get from a diagram which has j to the 2n. And then there is one more configuration in which you go forward with all the propagators except one of them. In one of them you go backwards. You go backward exactly by the equal amount. So you go forward with them that much, go backward with them the other one with the same amount. So going backward costs you a power of x, but because you are coming back to the same point, so you get no winding contribution. And in this case also this point is not fixed, you can change these positions, you can, and
Bubble back again. But eventually you have to go once around.
no, you are not going, your winding is still 0. You go forward with these propagators, with all other propagators, and come back the equal amount with the flipped one. So you are not picking up any factor from the winding, but because of going back you get a factor of x from there. So this is, we are calculating at only order x. So then again you get, because of these things are free, then you again get a power of beta to the n from these diagrams. Right. So these are the only contributions that are leading in this limit, and then we can sum these contributions and write the effective potential for, this is the contribution of holonomies from the fermions through integrating out, which is the free contribution and the interacting contributions. So we can systematically sum up all the circle diagrams of this form, not of that form, because these are the dominant in this limit. We can calculate up to arbitrary order and sum it up and rewrite the effective potential in this form, where if you notice, then it has the same holonomy structure as the free answer, namely this product of different.
You're computing psi dagger with some time separation. Can you go back? Just tell me, I got confused. I thought
This is the free energy computation.
Psi bar with some time separation, right?
So that, yeah. that was just free propagator. But what you're computing is the free energy as a function of Halder.
Okay, so at least for the propagator, what I was saying was right, that you just dress it. And then the free energy contribution, where you integrate out the propagator, the heavy quark, you're integrating out the quark also.
We are integrating out the fermion.
But if you integrate it out, then you just get some. I don't know, you don't get some effective theory where you. So everything is heavy for you. Okay,
But the holonomy degree of freedom is not.
is not heavy. So you're just investigating the effect on the holonomy.
Yeah.
Well,
How do interactions change all the conclusions about faster than exponential growth?
Okay. Okay. Go ahead.
Then at least for circle diagrams that we have computed faithfully, for them the structure of effective action for holonomy is of this form. This is just the form that we see in the free answer and corrected by some function which is of this form, which can be, so we are rewriting the free energy in this particular form, because j square beta by m is the quantity that appears in circle diagrams. So all the circle diagrams has this kind of contributions. With n melons it is like this. So we are rewriting the same series but in this particular form. This is very useful if j by m is very small and this thing is kept of something but fixed, does not diverge, then we can just truncate this series at the first order, namely k equal to 0, because for other things this is small, so they will just go away. So we have the sum of circle diagram is just H0, and then we ask the question that it looks like the free answer except that there is a function H0 multiplying it. So is there any mass distribution function that captures this effect? So in free theory the mass distribution function was a delta function. At the mass of the fermion you had a delta function. So you are turning on the interaction and then you are trying to ask the question, is there any change in this thing? Usually that thing is like it was peaked at somewhere and then it can broaden due to interactions. But then what we get after calculating this thing explicitly is that a collection of delta function and derivative of delta functions, they are like the mass gets shifted little bit of the width j square by m. So these are like delta functions, but still they are delta functions. So they do not get widened much larger than this.
I'm a bit confused. Your M label to begin with was a group, was one of your gauge fields. Is that what you know?
So
This is now a mass.
what's the whole holonomy thing was deforming the SYK model by turning on a mass. The mass is A. Okay, when the mass is very large, the theory is effectively free apart from holonomy interactions. And the previous part of this was computing everything for that free theory. Now he's turning on the first interactions, also in this scaling limit. The first interactions you have to get self-consistency, you have to sum an infinite number of graphs. You can do that. And then he notices that the effect of turning on this interaction is exactly the same as an effect of the following effects. Assume that all your fermions did not have the same mass, but there was a distribution of masses in your fermions. Just an algebraic observation. But this would give you the same answer.
For the holonomy effect.
For the holonomy effect. And the important thing there is the following, that had this mass distribution had a tail to very low masses, because we're going to very low temperatures, that would have had a disproportionately big impact on your free energy. Because the very low thing could have dominated. However, here this is not broadening it out very much. It just splits. It takes one delta function and splits it into a couple. But there's no continuous problem. So it just doesn't change the weight, at least to the order we calculate.
theory in J over M, right?
Still with perturbation theory in J over M. So we do all orders in J square beta by M, but perturbation theory in J over M.
I see.
The second thing, the first thing that we do all orders in J square beta by M is important because beta is, we're going to very low temperature, so beta is large. So it's important to be able to control that exactly.
I mean, but, okay, it would have been strange if I'm not sure what you expected, but, I mean, you wouldn't expect your behavior at very low temperatures to change if you kept some finite M effect. I mean, would you? I mean, you would still.
Yeah, I'm not so sure because you see that J square beta by M can be pretty large. So there we have to do all orders. So it wasn't so, I mean, it wasn't totally clear.
Even though J over M is small,
Small.
J times beta is large.
Yes. So this is a result of summing an infinite number of graphs. And the fact that the delta function changes to just a couple of delta functions is a very particular property of the answer. Now I don't know what exactly, we haven't carefully thought of what other possible, had it been something else, what would have meant that much.
I'm just thinking, oftentimes when you have these two kinds of scales, then you do an RG type of analysis. You thought of integrating out the mass at an energy scale of order M. Then you get some effective field theory just for the holonomies. Then in that you go to J beta, very large. Then thought of that way, would you?
Yeah, probably. Probably not. Probably not.
Okay, but I see your point that it's not obvious because they're coming together.
Right.
Okay. Can I just take a 5-minute break? And then
It's
I'll
almost
just come back?
finished, yes.
Oh, you're almost finished?
Yeah.
But that means what? At least some conclusion.
Okay.
Is it possible?
Take
Just
5 minutes.
2 minutes.
Okay.
I got to run to the rest.
Okay.
Sorry.
Fine.
I'll be back in exactly 2 minutes.
Yes, fine. So should I go?
Okay, wait for a second.
Okay. So because I have got some free time, I should discuss something else. What should I discuss? I'll discuss a little bit about how to get this effective action starting from that
Maybe
action.
ask me that question.
Oh yeah, if there are any questions.
I missed the whole part from this whole part where you mass deformed. What was the end conclusion? I mean, why did you do it? And just give me a summary. What did you learn by mass deforming the theory?
So by mass deforming the theory, you are able to calculate the density of states, and you could count the gauge singlet state that you are getting. So you mass deformed the theory and calculated the density of states.
Could I add to that? You see, the whole point of ADS-CFT is that you've got a theory with a large number of degrees of freedom, and yet your low energy observables are finite in the sense that they don't go to infinity as n goes to infinity. Now it's a very important question. So this, going to Witten's model turns it into a regular ADS because there's a Gaussian.
Yes.
Okay? So now there's a very important question, which is what is the growth in the density of states of your low energy observables?
Yes.
Okay? It's not order n, it's order 1, but it grows with energy. How does it grow? This is sort of important. In weakly coupled gauge theories, we know how that grows. It's exponential. Okay? And that was a very important qualitative indication that ADS-CFT was correct. Because that exponential growth is the same as the growth of a weakly coupled string theory. This is Hagedorn. Now this is a new kind of beast, right? Because there are many indices. So you can ask, how does this growth go? Or is it something familiar? Now, doing this calculation at the at the interacting point turns out to be very difficult. It's probably possible, but would have required more months investment than we would. Okay?
Interaction, gauge interaction.
Yeah, exactly. This J.
Yes.
Okay? So what we wanted to do was to deform this model to a place where we could easily do the calculation without hopefully throwing out qualitative features.
Okay.
So what we did was to take the fermions, which are massless, and turn on a mass.
Okay.
And make that mass large compared to J. Now J is a dimension, full parameter.
Huh.
So the effective coupling of the fermions in this theory is effectively J by M. There's a J by energy scale, but there's no energy scale in the
That's kinetic term.
yeah, there's no energy scale in the problem smaller than M because they all have mass.
Okay, okay, right.
Okay? So you can integrate all the fermions very easily.
Hmm.
But there's still an interacting mode memory in one of them.
Yes.
So you can do that calculation.
Hmm.
And there we did the calculation and found how the growth works.
Hmm.
The point is that it's faster than exponential. Okay, that is the main qualitative.
So, but we are away from the theory that we wanted to study, right?
Yes.
So
Yes.
this gives some bound. I mean, what type of bound does this give on the?
Yeah, that's it. I don't know. This is
No, sorry. So maybe what does this deformed theory tell us about the growth of the original theory?
we don't know. We don't know.
This is just.
This is just that with this structure of gauge interactions, in a place where you keep interaction small, this is how it works.
In a place where you keep the interaction small.
This is how it works. And then we can compute with the first effective interactions, and we saw that it didn't change.
Okay, so mass deformation is to give a parameter so that the
You
interaction
can solve it.
makes sense.
Yes. Okay, so we deform the theory to where we can solve it.
Hmm.
There you see the first order perturbation, you see it. What actually, if you go all over this, but
And then with this corrected form, because of interaction, we can go and calculate the same thing that we did for free theory and calculate entropy as a function of energy. Nothing much changes. It still remains as e to the e log e, the density of states.
you want to give some conclusions?
So yeah, so after working with this thing, you can get to the fact that if you have a bulk dual to this thing,
And just and the mass was not entering in the prefactor of the E log.
It's e by m times log e.
And what would have the original model, maybe this is what was being talked about, sorry. The original model, say of Witten or whoever, was n equals 0.
M equals it.
And
Yeah. So now there are two possibilities. One that I don't know what the original will do. It's much more complicated. One possibility is that theory effectively develops an effective mass, but it doesn't sound like it does because it's conformed. Sorry. Or maybe for this purpose. I'm not sure. I'm just what
it's hard to do.
hard to do the calculation. I think it's a doable calculation eventually because this gap equation can be solved. However, when we in our discussions, it looks like at least I think we would spend several months. Right? Yeah.
Which Schwinger-Dyson equation for this thing can be solved. I mean, these days do it numerically.
Right.
Doesn't understand.
Yeah, but suppose we're interested only at very low energies. Then they're able to solve it. Yeah. I think that we could make real analytic progress on this problem if we can.
Just to understand, so we are interested in the microcanonical ensemble, partition function, whatever. So you want to solve the gap equation and then put it back in the action.
Yeah. In fact, he had Indranil had an action, action for Green's function and self energies at some point. Okay. You want to solve the gap equation that follows from that action, but now with twisted boundary conditions, and then plug it back into that action. That's the mathematical problem. And it's a problem that we're solving order by order in perturbation theory at large mass. Yeah. Because these guys are able to solve that gap equation in the absence of holonomy at very low energies, I think we should be able to solve it eventually. So I don't think it's an totally undoable problem. However, maybe I can say one more thing. The fact that this growth is E log E has a simple intuitive explanation. Okay, which is this: what you're doing is trying to count singlets of this trifundamental thing. Now, counting singlets of this trifundamental theory is something like this. You bring down m copies of your trifundamental and then contract indices however you can. But this is exactly the same problem as the following. Oh, very closely related to the following.
So bring down m copies.
Of your
M
psi.
is the number of gauge groups, right? No, what was
Sorry.
m?
No, so let's say the gauge group is
Is
3.
3. Okay.
Okay. Now you can ask, how many singlets can you build with m size?
Okay, I see.
That sounds like a reasonable question.
Mm-hmm.
I'm trying to give an answer, but I think the answer is going to be the same. Okay, just intuitive. It's not attached. Okay. Now, each psi in the low energy theory carries a fixed dimension. So it feels like the operator which has m size should be higher and higher dimension. Okay. So it sounds like a reasonable question to ask: how many operators can you build with n copies of psi? Now you just have to contract the indices. Now I'm going to give you another an analogous problem that's very simple, which is consider a field theory with 3 fields, phi 1, phi 2, phi 3. The vertex in this field theory is phi 1, phi 2, phi 3. Okay? And then you look at graphs with n copies, with n vertices. This will involve basically the same contraction structure as we have here. Because every phi 1 has to contract with some other phi 1, that's like the contraction of indices. Okay. Okay? And then the fact that this problem is well known to grow like m factorial, number of such graphs grows like m factorial, is basically the thing that basically, this is the effect of. So, even though exactly the question we're asking and so on will be hard to answer in the interactive theory, the question that you're most interested in the interactive theory is, what is the number of gauge invariant operators as a function of dimension? That feels like answering the question I just posed, and feels on intuitive grounds to have the m factorial. Right? Because each psi has a fixed dimension. So bring m size, it's like having m of those. Of course, there's some anomalous dimensions and all, but hopefully that's not very important.
1 by n.
Yeah. Okay. So now you have to contract, and you get an m factorial. Seems like a very simple intuitive reason. For this reason, I don't think it's wrong even in the.
Well, why is the matrix theory different?
Say.
Why is the matrix theory as opposed to the trifundamental different?
Why is it? Because in the matrix theory, you have only 2 indices, so there are no interactions.
So you can contract them pairwise?
Yeah, it becomes a chain.
It becomes a
Chain. It's a bunch of strings. It's basically the difference there is that the effective thing is not an interaction but a kinetic in your effective field theory. Because it's quadratic. It would just be phi 1, phi 2. Okay, and so this whole Feynman diagram something would be totally and actually if you estimate the coefficient of the effectorial from this argument, you get the right coefficient. So I think that this is basically at root what's going on. And said this way, it doesn't sound different from the J equals infinity theory. So it seems to me that in the J equals infinity theory, if I had to make a guess and ask how does the number of gauge invariant operators grow as a function of this dimension, I think dimension factorial seems like a very reasonable guess. This is the guess I would make. But to make this precise, you have to be able to control all the anomalous dimensions. And it's a hard thing to make precise. That sounds intuitively very good.
I see.
I don't think we put this in our paper.
So as a conclusion, we have these things. When J is large enough at J equal to infinity, you have new set of light modes which are very large in numbers, and their contribution to the 4-point function does not grow as exponential in time, but they nevertheless dominate for small values of time. of the order log n, and the other conclusion is that if you calculate the theory when j equal to very small, and then you calculate the density of states, then it has larger than Hagedorn density of growth in density of states. And we have also seen that there is this Hawking page kind of transition, and when even when you have gone to black hole saddle point, there is this maximum of the saddle point that keeps floating there. It is still there.
Hawking page happens not at temperature of the order 1, right?
No, it happens at temperature order log n, 1 by log n.
Because of the light states.
This is in the mass deformed theory, so there is no light states.
Oh.
It's just because n such, but yeah.
What you can
It's just because you see, Hawking page is a competition between the fermion degrees of freedom and the measure. Fermion degrees of freedom are, let's say, n cube, whereas the measure is n squared. The measure is temperature independent, but the fermion degrees of freedom depend on temperature. So it's where they compete is when temperatures are very low. Okay, which means that the black hole type phase dominates for all reasonable values of temperature. Greater than 1 by log n, black hole type phase dominates. However, lower than that, this other phase dominates. Now, why is that interesting? For two reasons. A, it has great implications for the microcanonical answer, for energies of order 1 or order n squared. And B, it sometimes happens that subdominant saddle points, though exponentially suppressed, could contribute important effects that might be relevant for unit area. Even if you're at a temperature where the dominant contributions might be. Do you know what I mean?
I didn't get the last part.
I should be talking.
yes, please.
Okay.
No, it's fine.
Let's suppose we're at a temperature order 1.
Yes.
Okay? And we want to compute some correlation functions as a function of time. One of the apparent contradictions of the unitarity is the fact that 2-point functions decay.
Yes.
That seems impossible in a unitary theory, and you want to know how finite n effects can cure that.
Yes.
Okay? One possible thing that has been suggested before in similar contexts is that even if you have a saddle point which for free energy purposes is subdominant, it could become the dominant contribution for calculating 2-point functions once time becomes large enough. Simply because in the dominant saddle point the 2-point functions decay exponentially, whereas in subdominant saddle points it may just take oscillate. Okay? So the question of whether a saddle point is dominant or subdominant depends on what process you're calculating. And if you're interested in processes which are 2-point functions at times of order n, then this could switch.
Yes.
So the fact that this other saddle point exists, at least in this mass deformed theory, is perhaps may play a role in analyzing unitarity questions at this stage.
This is it.